Hi, my name is Pranav, and this is my project about testing noise-to-noise learning with encrypted images. So first, what is noise-to-noise? Noise-to-noise is a method of image restoration that uses noisy pairs of data instead of the traditional noisy clean pairs of data. This works since the L2 loss function that is used in the model only requires that the pairs have the same distribution of noise instead of having a perfect data set. And the original researchers found that training with noisy pairs was in fact quite effective and in some cases even outperformed noisy clean pairs of data. So why test with encrypted images? Strong encryption is the cornerstone of modern communications, and being able to crack any of the modern encryption algorithms would have disastrous consequences on the entire world. Badly encrypted data is especially susceptible to being cracked because often the overall pattern of the data is preserved even in the encrypted image, which we can see later on. And additionally, if a small byte error happens, for example, if one byte is changed in the image, this usually propagates to a much larger error when the image is decrypted because of how encryption algorithms work. So an example of bad encryption is the classic ECB penguin. So using AES encryption, which is a modern standard for encryption, if you use electronic codebook mode, which is a one-to-one map of a set of decrypted pixels to encrypted pixels, you can still see the overall pattern of the data within the encrypted images. So we can still see like the outline of the penguin. But if you use block cipher mode, where each block of data in the original image does not have a one-to-one correlation with encrypted data, the image is much more random and it's much more secure. And for an example of byte error, in each of these little areas, only one byte of data was changed slightly, but that resulted in there being a much larger effect on the overall image because of how encryption algorithms work. So for my implementation, I used an unofficial implementation of noise-to-noise, as it had a significantly lower training time than the original implementation. The original took about 8 hours to train, and the unofficial implementation took about 30 minutes to train, which allowed me to do a lot more testing. It used a convolutional neural network along with an L2 loss function, and it was trained for about 60 epochs. And I added other noise models for training, such as two forms of AES encryption, ECB mode and CVC mode, block cipher mode, and adding small byte errors in encrypted images shown previously as a noise function. The datasets I used in this project were BSD300, where I used 200 training images and 100 test images, and I also created a custom clipart dataset because that was more useful with ECB encryption, where there were 88 training images and 51 test images. The metrics I used to evaluate how effective the denoising was the peak signal to noise ratio, which is used to measure the amount of noise present in an image, and it's usually expressed in decibels. So in this case, a higher PSNR value is better than a low one. And then also the L2 loss function as discussed previously. So denoising the ECB encrypted images gave us a PSNR value of 15.53 and a loss of 2100 with the BSD300 dataset, and with the clipart dataset, there was a PSNR value of 12.56 decibels and a loss of around 5400. So we can see the loss and PSNR values over the 60 training epochs. And as you can see, the PSNR values are quite low and the loss values are quite high because of the randomness in the data, which means that the model is not that good and there's not much to note. So some examples are of the original image and an encrypted image, along with the predicted image. As you can see, not much happens other than the outlines of the image becoming a little bit more pronounced in cases where there's a large amount of white space or solid colors, but in cases where there's not much of that, really only the tone of the image changes. With the clipart dataset, you can see that the overall image still stays constant, and the denoising really only changes the tone of the image, though the duck does seem to be a little bit more yellow. And so denoising errors in the decrypted image. So I tested noise-to-noise and noise-to-clean with the byte errors in the image. And over the 60 epochs with noise-to-noise, we see that it did have a higher PSNR value and a lower loss value. And in addition, it also stabilized at that value much quicker and stayed more consistent throughout. So some examples of this are the noise-to-clean prediction. We can see that the original image and then the training image, along with the predicted image, we can still see that there's a lot of specks in the sky. But with the noise-to-noise model, a lot of that noise was filtered out in the final predicted image. And then testing with different noise levels between pairs of data, we see that, as expected, if there is less noise in the original image and the target image, you get a higher PSNR value and a lower loss overall, which is to be expected. And in conclusion, we see that convolutional neural networks are not effective at denoising encrypted images, and this is mostly due to the pseudo-randomness of encryption algorithms. Neural networks and machine learning algorithms rely on there being some way to predict the output based on the input, but since the input or output, the output is pseudo-random, there's not really any way to predict based on random numbers. And it was only slightly effective when there were large patches of solid colors in the image. Noise-to-noise and noise-to-clean models are both highly effective at denoising decrypted images though, and noise-to-noise was marginally more effective than noise-to-clean, most likely because it didn't overfit the data as much because of the noise present in the output dataset.